Cindy Kelly, Atomic Heritage Foundation. It is Wednesday, April 25th, 2018, and I have with me Tom Cormier. First question is, please say your full name and spell it.
Tom Cormier, Cormier.
Perfect. Okay, my first question to everybody today has been to tell me a little bit about yourself, where you're from, when you were born,
Yes.
your education, and how you came to be a scientist.
Well, I grew up in the suburbs of Boston, in the town of Lexington, which is a very historic area in its own right. And growing up there, I was surrounded by people who in that community lived and worked in and around Boston and many of the big universities in the Boston area. In fact, a lot of the neighbors on my street were from MIT and so forth. And my father, who was very interested in science but was not a scientist, he was a kind of an engineer, but hands-on sort of a guy. He always talked about physicists, even when I was very young, because he grew up, of course, through the period where, from his perspective, physicists helped, with the existential crisis of World War II and so forth. And so he was very impressed with physicists, and so he would always talk to me about them. And although he really understood almost nothing from a fundamental point of view, he really wanted to hear about it all the time. And so I sort of researched things. Even I can remember even being very young, researching things and trying to help explain it to him and so on and so forth. And finally, when I got older, I just went to my neighborhood school, which was MIT, and the rest is sort of history. Yeah, and at the time I arrived at MIT, which is 1967, I first arrived there. Every significant university in the United States had a burgeoning program in nuclear physics already at that time. It was something that also grew out of the Manhattan Project, that it sent its roots out into the university system in the United States. Virtually every university in the United States of any size had its own particle accelerator in those days. And so as an undergraduate, you were invited to get your hands into the physics and work with these machines that were all over the place. Now, of course, over the years, those machines were turned off gradually, and the science got bigger and bigger and bigger until finally you don't find the kind of science we do anymore on a university campus, that's for sure. It's sort of, the science has sort of outgrown that, but I've been attached to it right from those early days.
So, how did you, what happened next? What happened between MIT and ORNL?
Well, I had the usual few postdoc positions. I spent a year in Germany at the Max Planck Institute, and then I got my first faculty position. And as often happens to young assistant professors, the way you get promoted is by moving to another university. So I had tours of duty at several places until finally I had become a senior professor and got invited to join the faculty as a department head, and worked as a department head for a number of years until finally a position opened up here for a new group leader to give the effort in the kind of physics that I was doing. So we call it heavy ion physics, but I'll have to explain why in a bit. But there was an opening for a leader in that area here at ORNL to sort of rejuvenate the effort and give it a new focus. And so I thought it would be interesting. I was, at the time I came here, probably officially past the retirement age, let's say. So I was looking forward to working for whatever, 5, 6, 7 years or so, and taking this challenge of instituting a new program and seeing what we could do with it.
And how many years has it been?
Been five years so far, yeah.
Mm-hmm.
Yeah,
Great.
and I would say that we've really accomplished most of what we set out to do in that period. We've hired a lot of new people and built up the group, as you know, at CERN, and got the necessary rules waived to allow us to cite our people at CERN. So the group literally is in Geneva, Switzerland, although I'm here most of the time. One week a month, roughly, I go to Geneva. So
Well, can you describe in very simple layman terms what it is that your group is involved in?
Right. So we use the Large Hadron Collider at the CERN facility. The CERN is the European Center for Nuclear Research, and all the European countries come together there to conduct their research in this field, elementary particle physics and high energy physics. And by pooling their resources, they're able to, build an impressive facility, a world-class facility. It's said to be the largest physics laboratory in the world. And so today, not only Europeans come there, but also a very substantial number of Americans, for instance, and Asians come there to do their work. And so the kind of experiments that are mounted on the Large Hadron Collider typically have thousands of collaborators. The ALICE experiment that I'm part of has about 2,000 collaborators. That is, when we publish a paper, it has 2,000 names on it as the authors of the paper. So it's a significant undertaking. The other experiments are even larger than that. In fact, there's some that are approaching 5,000 authors, I think. So it is definitely big science. Obviously, this doesn't fit on a university campus anymore. And in fact, it almost doesn't fit in more than one place in the world. The whole world comes together to do this in one place, and that's what CERN is. Now, at this facility, what we do is we collide elementary particles. My specialty is colliding whole nuclei, whole lead nuclei, circulating around this accelerator in opposite directions at really unprecedented energies, are brought into collisions as a means to produce tiny samples of ordinary matter heated to trillions of degrees centigrade and compressed to hundreds of times the density of normal nuclei to essentially turn back the clock. This tiny sample of matter is similar to, it turns out, what the matter that made up the universe was like when the universe was only a few microseconds old. So it's basically using that facility and those special ions gives us a window into the nature of the matter that filled the universe when it was only a few microseconds old. To push further back than that, to try to push back right to the very beginning, is essentially impossible because the laws of physics are even unknown to us under those conditions. But this time window, which begins at a few microseconds after the universe began, is essentially something that we can understand with the current laws of physics that, as we understand them, and an area where we can actually make observations of the matter by, as I say, running back the clock through these collisions.
So why don't you tell us a little bit about the most famous recent discovery, the Higgs boson?
Yeah, the Higgs. So the Higgs is an amazing discovery, as you said. It's one of the few examples in physics where you built a facility and then within the first year of operation you've won the Nobel Prize with the three scientists to whom it was awarded. That doesn't happen very often, I'll tell you, that thousands and thousands of people came together to build that machine, and it was a very single-minded effort in that sense. There was one thing that everybody was striving for. It was to see if this particle existed, because it was a missing link, essentially, in the theories that underpin our understanding of matter. So the theorists told us it had to be there. If it wasn't there, then our understanding was really incomplete in some very fundamental way. And so it was worth the I don't know, $5 to $10 billion that were spent to accomplish that result in the end, to build the biggest machine that has ever been built anywhere by human beings, and to operate it during the first year in a way that gave positive evidence for the existence of the Higgs boson. What the Higgs boson does in the theories that describe it, it's rather complicated, but what it does is it gives everything mass. Without the Higgs boson, all the particles that we understand in the universe, all the atoms that we see around us, they would be massless, and it wouldn't be much fun. So finding the Higgs was really important to having everything hang together. All the bits and pieces that make up the stuff around us that it has any substance at all is really due to the Higgs boson. So it's there, and it's there, and in fact it's amazingly simple once you see it. It stands out. It's obvious. It was just out of reach for all these years until we built a machine big enough to find it.
It's so interesting.
Mm-hmm.
And as a souvenir there, I bought a coffee cup
Mm-hmm.
that has a simplified version of the formula.
Yeah.
I mean, it makes
Right.
it look very simple.
Right. Yeah. It's
And I know it's
it's
not.
not simple. No.
I know it's not.
It's very. In fact, that I think what you're talking about is the Qcd Lagrangian, is what it's called, and in fact, you can write it down, but you can't actually solve it in detail because it's a highly what a mathematician would call nonlinear formula, and there's no way to actually solve it exactly. Now we can solve it approximately in computers, which is what the theorists do these days. But it's a beautiful formula, but basically too complex to really figure out with a pencil and a paper. Well, so the people who did the experiments to discover the Higgs and so forth are really working in somewhat different field from me. They collide protons, and it makes all the difference in the world whether you collide two protons, which are the smallest pieces of matter that you can isolate, ordinary matter that you can isolate, or the things that I do, which are to collide full lead nuclei. And start with a large sort of macroscopic sample of matter. Now, in the people who are studying the Higgs are looking for the sort of the next piece of the puzzle, which would be if there are more examples of the Higgs boson. Is it really only one? Are there multiple Higgs bosons? Because those are variations of the theory which would make the universe behave quite differently. And so there's this exploration of the so-called Higgs sector is looking for the kinds of physics that might be hiding in the neighborhood of the Higgs. And now what this takes, so as I said, we discovered the Higgs in 1 year. What this takes now is many years' investment, studying in much, much greater detail the kind of events where the Higgs shows up, but looking to see what else is going on, maybe at a 1 part in 1,000 or 1 part in 100,000 kind of level, and digging deeper and deeper into the details. So that's good old-fashioned, roll up your sleeves kind of science, and that's what's going on now.
That's what they're doing.
Yes.
But what you're doing.
Yeah, so now we collide lead nuclei, which is something that CERN does 1 month a year. So they dedicate, and it's actually possible to distinguish it by saying what the people who are colliding protons are doing are studying elementary particle physics, the physics of the elementary constituents of nature, whereas what the people who collide lead nuclei are studying is an extension of nuclear physics into this ultra-high energy regime. And so 1 month a year, the accelerator runs for about 7-8 months a year. And so for 10, 12, 15% of the time it does nuclear physics, for the rest of the time it does elementary particle physics. And in the program of studying the nuclear physics is what I began my dissertation with here, which is to study the matter of the early universe. By colliding two lead nuclei at these fantastic energies, you create not a point-like object, which is what you get when you collide two protons. You create something that actually has a finite volume. A nucleus may not be very big, but compared to a proton, it's gigantic. So what we do is we take a sample of matter the size of a lead nucleus and heat it, as I said, to trillions and trillions of degrees until the matter melts into a soup, which is very much like the early universe in the first few microseconds of its existence. And then our detectors help us study the properties of that matter and observe it as it expands and cools and turns back into ordinary matter. So we can trace it from the instant of the collision, where the temperature goes from essentially 0 all the way up to trillions and trillions of degrees in the collision, and then watch the collision come apart in our detectors. As the matter cools back down, it can watch the transitions that it goes through, the same transitions that the early universe went through, where the early constituents of the universe was this soup of quarks and gluons at very, very high temperature, which expanded. The universe expanded through its first moments of existence, and as it expanded, it cooled in the same way that our little mini bangs expand and cool when we perform these collisions at the Large Hadron Collider. So we can study how ordinary matter reappears from the start with these collisions that create the matter of the early universe, and then study it as it reemerges as ordinary matter, and what kind of matter is made. We make the protons and neutrons, for instance, that make up everything around us today, appear in our collisions. So we start with matter heated to trillions of degrees where there are no protons and neutrons. There are only quarks and gluons, and then we watch it cool and expand, and we watch the protons and neutrons emerge again from this hot soup, just the way they did from the early universe. So it is really sort of an experimental probing of how the universe behaved in that first few microseconds, which we can then compare with the theories of the early universe. Now, these theories of the early universe obviously are very closely coupled to our other colleagues at the Large Hadron Collider, because this is a world that was full of elementary particles. So you have to know how elementary particles behave. I shouldn't have given the impression that we only work 1 month a year when we're running the lead beams, because we have to understand the collisions of the protons as well. It's an important ingredient in understanding how those protons emerge when we study them with the lead collisions. So it's a full 7 or 8 months a year that we're doing physics in Geneva. Yeah.
Well, that's fascinating.
Yeah.
So your team is actually, collaborating with members of other teams that are dedicated to the particle physics, but
Yep.
yeah.
Yeah.
Yeah. So do the particle physicists bring in members of your team, or is it a bilateral?
It is, and in fact, all of the experiments, there are 4 experiments on the Large Hadron Collider, and they are sited at locations where the beams intersect. The beams at the Large Hadron Collider has a circumference of about 21 kilometers, and as the beams go around that enormous ring, they collide at 4 different locations, and at those locations there are these enormous experiments, and each of them studies the physics of these collisions from a slightly different perspective. That is, the detectors differ in the way they perform their observations, the kind of things that they measure. So there's a coherence in that the underlying physics is the same, but everybody is looking at it in a little bit slightly different way. And so, yeah, there's a very strong sort of crossbreeding between all the experiments and all the collaborators. Yeah. So one of the things I do sort of in my spare time is I'm on the so-called Alice Thesis committee. So we have, as I said, about 2,000 collaborators. Among those collaborators are hundreds of PhD students, and those PhD students write their PhD theses. And there may be as many as 50 PhD theses produced per year just from the Alice experiment. Right now, and then the students are invited to submit their thesis to be judged, for the annual prize that goes out for the best thesis in Alice, for example. So I'm one of the guys who has to read all of those submitted theses. This year we have 20 PhD theses, so that'll keep me busy till about July.
Do you actually meet with the scientists, or you just read the paper?
No, we know most of them. The young people are really the heart of the experiment. They do all the work, right? Mm-hmm. So they are. You can't miss them. They are there in the Alice buildings, and they are underfoot, and they're there, and you know them well, and you know their work. You've known them for the 3 or 4 years that they've been doing it, and so yeah, they're well known to us, and. It always comes down to a difficult choice. We have a committee, I think, of probably 8 people this year who will look at these 20 or so theses that are submitted and try to judge the best one out of the bunch. Yeah, it's a difficult job. But we use, and again, every thesis is a little different. Everybody has a PhD thesis asks a question basically, and then the author of the thesis tries to convince you that he knows the answer or she knows the answer. So, but everybody has a different take on it, and so it's quite interesting to see how the young people are sort of continuing this kind of tradition of nuclear physics, but now on such a mega scale that it's, when I was a student, it would have been inconceivable that you could have a machine this big and you could actually make it work, and never mind make it work, but just imagine collaborating with 1,000 people and getting anything done, right? Getting that paper written when there are 1,000 authors is a task in itself.
Yeah. Staggering. Goodness, and on top of that, you're dealing with, I'm sure, people from every nationality.
Oh yeah. So it's a yes, it is a. So in Alice there are, I think, represented about 50 to 70 separate national funding agencies, for example. So it operates a little bit like a United Nations, a mini United Nations, to make all of those people focus on the same idea, right, and cough up the money to support their share of it and so forth. So the Department of Energy is one of the participants in that. They fund our work explicitly, but they're also stakeholders, and they contribute to running the experiment. And so it is a little bit like the United Nations, figuring out how much is your share and how much is my share, and so on and so forth. So yeah, and within that group of 50 to 70 or so national funding agencies, there are some that are dominant, that they simply are the largest participants, and they are, they include the ones you would guess probably, the United States and the major Western European countries, and Russia and China, of course, and Japan. So all of the basically all the countries that have very vibrant economies can sort of afford this kind of science, and so they tend to be the leading groups in all of this. So but every country, virtually every country, is represented at some level, even if it's only a single person. I guess Azerbaijan is there, for instance, and they have one student who's part of the collaboration. So you're right, every nationality is represented at some level, and some nationalities are more dominant, of course, and as I said, they tend to be the ones that come from the countries with the very strong economies, and can kind of afford it. But yeah, and it makes it well. The common language in all of the scientific communications is English, and but if you're in the experiment, you're hearing Italian and German and French spoken sort of simultaneously. It takes a little getting used to, actually, all that background noise in 5 different languages all at the same time. So, but the scientific communication is in English, and the papers are written in English. I mean, there was some debate probably very early on when CERN was first formed whether it should be English or French, but English won out. I think official CERN communications are still in 2 languages. That is, when they sort of send out some political document, the top half is in English, the bottom half will be in French. But all of the real scientific discussion is in English. So,
which is a big advantage for Americans.
Oh yeah, really. Because if I had to survive on my French, I'd be in trouble.
That's right. Oh goodness. So I'm just curious about the number of women who might be involved in CERN work.
Yes.
Just if you don't know precisely.
No, I don't know. I don't know precisely, but I'll tell you there are some interesting trends that you can observe. For instance, women are a substantially larger fraction of the scientific community at CERN. If you look at the collaborators who come from France, for example, same is true of Italy to some degree. Women in Italy, tend to gravitate more toward physics than women in the United States do, for example. So I'm trying to think, in the U.S., the full U.S. team, not just Oak Ridge, but the full U.S. team consists of about, it varies from year to year because of the students come and go, but there may be 100 U.S. participants in this experiment. And I'm going to guess that there are less than 5 or 10 women in that group from the United States. Whereas the fraction for the French group might also be 100 people, but they'd be closer to half women. It's really big. Yeah,
so
it
Marie
is.
Curie lives on.
Yeah, I think, in fact, I think there's an influence of exactly that. That's right.
Well, what do you think the future holds?
Well, so this is a big topic of discussion, of course, because the Large Hadron Collider took approximately 20 years to realize. So the planning for it started, 20 years ago, and the building of these big experiments takes 10 to 15 years, even once you know what you're going to build, and you need to get the funding in place and so on and so forth. So there's a 20-year commitment to getting this machine running. So the planning for what comes next is started quite some time ago and already, and there are a number of options on the table. It doesn't cost a whole lot of money to explore options, but once you select one, then it gets expensive, right? So there are options. There is a so-called future circular collider. The Large Hadron Collider, as I said, is a circle about 21 kilometers in circumference. So the future circular collider would be about 10 times bigger than that. So it would cover a substantial fraction of the western end of Switzerland and that region of France, and would have an energy that would be 10 times higher than the current energy. There are other ideas, however. There's the so-called compact linear collider, which is where you basically give up on the idea of running beams in a circle so that you can sort of reuse them, but rather make accelerators that are linear, straight lines, and they simply just shoot particles at each other. Now you can have a machine that maybe is 100 kilometers long, and the beams come at each other like the bullets from two guns traveling in opposite directions, and you have collisions like that. And so each of these approaches has their own team pushing for them and so forth, and R&D is going on in both kinds of futures. But again, these are facilities that are so big. We're talking now, 10 times the scale of what has just been accomplished, right? This really now takes complete involvement of the whole world. It's not so. Whereas the U.S. Participation in the building of the Large Hadron Collider was, at the level of some percent, probably, of the total budget for the thing, although there was a very significant technical contributions from all the national laboratories, for example. But it would take from the major economies of the world far more substantial investment to realize now a facility which is 10 times the size of the one that we have now. So, all the usual problems then have to be worked out. Where are you going to build it first? The Japanese would like to have it in Japan, for example, right? And the U.S. senators would like to see it near Chicago, or and so those discussions will go on forever. And at the end of the day, the country that comes up with the most money probably has the most to say about where the thing gets built. So, but the future is because the lead times are so long on these projects. People are already thinking about what will happen now 10 years from now, 20 years from now. I think there's one thing I would say, just to maybe to sort of frame this kind of work. It's a little bit different from a lot of the science that your typical high school student may think of when he or she thinks of science. They think of the chemistry laboratory and behind the little door and so on and so forth. This is truly big science. This is science of the scale of the Apollo lunar landings, for instance, where which was undertaken, of course, entirely by the United States. But now the science of this size is of such a scope that it really needs to be undertaken by the whole world together. So that's an important part of this, I think, and that attracts some people to it. It pushes some people away because they just see it as so much chaos, right? So there are long periods of chaos. There's no doubt about it. But in the end, when it all comes together and works, it's really quite impressive that you can really get that many people moving in the same direction. And so it's it's an exercise really in sociology as well as science, which is kind of fun.
Well, in a way, people talk about, can we have another Manhattan Project?
Mm-hmm.
And World War II was such a galvanizing force.
Right, exactly.
Right,
Yeah.
and you had all the prima
Right.
donna scientists
Right.
that Oppenheimer had to corral.
Right.
Some of them were a little wayward, but most of them
Right.
were
Right.
very focused.
Right.
But that's very hard to recreate.
Right. Well, but it's exactly right. And there's an interesting outgrowth of that, is because what I call big science actually begins with the first example of that is the Manhattan Project, because prior to that, governments around the world did not invest in science at all, and you had private foundations or universities or whatever investing in science, and that really limited the scope of what you could do. But as soon as, after the Manhattan Project, it became clear that the way to really get things done is to put the backing of major governments behind certain scientific initiatives, then you can see what you can land on the moon. You can build the Large Hadron Collider. So that really begins with the Manhattan Project. This whole idea of government investing in science really came out of the Manhattan Project.